we are discussing tunneling spectrum in a normal to superconductor or superconductor to superconductor junction. And first what we did was to look at the tunneling between a normal and a normal state, and then we found out that it is ohmic, that junction is ohmic. Now what we are going to do is to look at the tunneling between normal to superconductor, and we have just seen that you cannot have the tunneling unless your EV, the voltage times charge EV matches the energy of delta. So, so delta is the distance of the excited level from the putative Fermi level, and then that is so in terms of pictures. Yeah. So, this is the picture. So, your delta is here, and you have to supply, your EV has to supply this kind of energy. Okay. So, this is normal to superconductor tunneling. And this one is the superconductor to superconductor tunneling. So, look at both sides, you have this density, superconducting density of states, and you are tunneling. Here is on the one side you have continuous states which are normal metal, and on this other side you have this gap, and there is a large state here, density divergence on both sides, right, and these are occupied, these are unoccupied. So, from Fermi level or chemical potential, you have to supply this amount of energy that has to come from this EV to give you the tunneling. This is actually intuitively quite obvious, and that is what your calculation also shows. The thing okay, so let me show you some picture first. So, this is the current versus voltage, for example, and as you can see that the normal one is this one dashed one, whereas the this one has a gap. The normal to superconductor tunnel junction gives you a, so there is no current till your voltage hits delta by E, okay, and then it starts picking up, and then it becomes after that it becomes linear. The other thing which we will come to is something interesting, which is the differential conductance dI/dV. So, from that same expression you can now just take a derivative, and the only place energy appears, voltage appears is here inside the Fermi function, and so you just use this derivative, and again we know that the derivative of Fermi function has a bell shaped structure, right. Negative derivative of Fermi function has a peak structure. So, and the peak width is about 4 kT. So, in a region around 4 kT you will get this smearing, so called smearing, due to this peak, and that is so it is plus minus 2 kT. So, that the result therefore is that you will get a G. So, this is G N S equal to D I N S dV is 2 pi delta to the power half kT, and it actually follows the at t equal to 0, this has this just diverges, this goes up, and at just look at the structure, it is exactly like the density of states at t equal to 0. At finite temperature, of course, there is a smearing, and that smearing follows this curve, but this also tells you that there is a large pile up of density of states at EV equal to delta. This is the other curve that I just showed, this is the I versus V, and at t 0 then it starts from the solid line, which starts from EV equal to delta, and then it goes up. At t greater than 0 there is again these small carriers which are thermally activated, and they contribute even below delta. So, that is something that is expected, and that is exactly what you see, if of course BCS theory is correct, and these are experiments that actually sees that BCS theory, these experiments see that the BCS theory indeed is correct, it gives right results. So, this is a simplified picture, and d I d V basically follows the density of states on this side, and as a function of V, and this is actually true. I mean, this experiment is a very important experiment, tunneling experiment, and looking at the differential conductance to directly look at the density of states. It is a major experiment that one does in superconductivity. This is superconductor tunneling, and it has again a characteristic which is a bit different in the sense that there are these two gaps. So, you have to consider the two density of states at two energies, and then the density of states forms you put in, and then see where the conduction starts, and this is the picture. See, the INN is ohmic, and this one has this kind of structure. This is the ISS, okay, and there are for t greater than 0, of course, there are these excitations available, and you can actually check that there is this two sort of kink type structures at this is a kink type peak here at delta 1 minus delta 2 mod, and it starts picking up from delta 1 plus delta 2. So, your two gaps are there. So, your EV has to cross these two gaps, and it starts conducting at that point. But there is an interesting tunneling situation that is very specific to superconductivity, and that was noticed by Andreev. He showed that it is not, of course, those tunnelings do happen, but then there is another kind of situation that can arise, and that is very specific to superconductor. So, for example, tunneling from a normal state to a superconducting state in which such a situation will arise, and this is a brilliant intuitive idea, and let me just explain you in simple terms, and it is actually very simple. So, now suppose you had you have normally looking at a reflection of an electron from when it comes from left, strikes this interface and goes back to left. It is generally it is called a specular reflection. It follows the more or less these two angles are the same, and it goes back. So, it comes, hits it, and goes back with the equal angle. That is the usual story. Or it can enter inside with the, if your if you, as you saw in this other Giever's experiment, it can also go into the right with a exponential tail till nothing will go in until at 0 temperature, until your EV is equal to delta, then it will pick up. So, that is the standard scenario, and the other scenario is that it will just go back with a theta 1 equal to theta 2 angle. So, this is fine. But then Andreev argued, and he showed that indeed if an electron comes here, there is another scenario that is possible, that it suppose it does not have sufficient energy to enter, that EV energy to enter on the right, it can catch an electron at the close to the boundary and form a pair, and that pair can enter on the superconducting side. It is a Cooper pair. So, it goes in and becomes part of the condensate. But then since it caught an electron and then entered, you have to balance the charge. So, what happens is that a hole goes back to the left. So, the charge is balanced. Look at this, the see, electron plus electron is a pair. You can think of a pair as an electron is equal to a pair plus a hole. So, an electron comes, becomes a pair, part of a pair, and sends back a hole. So, that is everything is then satisfied. The thing that is different here from the above picture of course, the electron went back, but here not only does the hole go back, it goes back exactly in the same direction and path to conserve the energy, momentum, everything, right, and of course the charge. So it just retraces the path that the electron came through, and it goes back as a whole. And this is so this is what is shown here. An electron becomes a whole. So on the electron side, an electron came with charge minus e, with momentum k and spin sigma, and on the reverse direction a hole goes back with charge plus e, momentum minus k and spin minus sigma, so that everything is balanced. So this is called an Andreev reflection, and this is seen, and this is actually a terrific signature that you really have a superconductor with a gap on the other side. And it is a remarkable situation. It happens only from normal to superconductor transition. I mean, this scenario that I showed is normal to superconductor, and that is where it was seen. And this is an example why superconductivity is another example why superconductivity is so exotic, because you send an electron at the interface and you get back a hole which is absolutely retracing the same path on the left hand side. So you send a current and you get back a current, because hole moving to backwards is the same as current, so the current remains conserved. So this experiment has been done, and this is named after Mr. Andreev, he who first did it. There is an issue that I mentioned right in the beginning, and at least twice, is that the superconducting wave function is not BCS wave function is not an eigenstate of the number. Now, given that one can actually calculate the fluctuations in number, and one can actually show that the fluctuations for a macroscopic thermodynamic system can be negligible, and that is a very assuring thing, because otherwise you will not be able to do able to form superconductors, because the superconductivity will just fluctuate in number. The state that state will have such huge fluctuations in number that it will be difficult to do anything with it. So so what one can calculate, I am not showing the calculation because that is not necessary. It is just an information you can keep, that you can calculate the mean square fluctuation from. So this is from the deviation from the mean and square and average of that, and that gives you a number for about a typical system, which is a Avogadro number of particles. This delta RMS, which is square root of that, turns out to be about a billion. Okay, and then you divide this by n, then you will have 10 minus 13. So this is like a statistical situation in a many particle system. When n goes to infinity, for example, extremely large, and this will go to 0, and 10 minus 13 is already for all practical purposes 0, and the fluctuation, the fractional fluctuation goes to 0. So you can actually work with BCS wave function, and this is in a macroscopic wave system, then you can ignore exact particle number conservation, but one can actually go beyond this, and that is what one can do. From the BCS wave function, you can actually project out the fixed number part of fixed number wave function also. So suppose you want to find out the wave function, what is the wave function corresponding from here, which is the term that gives me, say, n by 2 pairs or n particles. Okay. So that can be done, and that was done by this simple trick that so what you do is that you add a phase to it. This UK Vk are they are not real, they may not have to be real, they are complex, and you can write a relative phase here, e to the power I phi, and then this is the BCS wave function, and then what you do is that you just multiply it by e to the power minus I n phi by 2, and then integrate over all phi. Now see what happens. For example, suppose your n is so n by 2 is equal to say 4. So, as you remember, there is just two case states k1 and k2, from which I found out that the state, there is one part of the wave function is one part, it was a linear combination of 0, 1 and 2 pairs. That means 4 particle state was there with the coefficient Vk1 into Vk2. So, that part of this wave function will have a phase which is e to the power twice phi, right. So, 2 into phi means 4 into phi by 2. So, this will give me e to the power n by 2 into phi minus this one which is 2 into phi into I, right. And then and we are integrating with respect to, so this is minus, we are integrating with respect to phi d phi, okay. And that will be what, because this will be just a delta function, and then that part it will be n by 2, it will be non-zero when n by 2 equal to 2, that means n equal to 4. So, by just writing it, choosing the corresponding n, I can find out that part of the wave function where there was, which is, so there was a Vk square here, Vk1 into Vk2, remember, and e2 into e to the power twice minus 2 phi, and I just pick out that part of this wave out of the entire set, which is a linear combination of all n by 2 possible pairs. I can just pick out the one I want by choosing the corresponding n. So, so by integrating over all values of phi, that means when you make phi now uncertain, is completely uncertain because you are integrating over all phi between 0 to 2 pi, and that means you are picking out a particular n. That means this conjugation exists, that when you when phi was fixed, then delta 1 was of the order of a billion. Now I am making phi unfixed, integrating over all phi is uncertain, then my n gets fixed. So, that means there is this uncertainty, it follows the uncertainty delta n delta phi greater than equal to 1. So, this is another example as that BCS wave function is a beautiful new kind of wave function. It is actually a coherent state, and it is a wave function that we have not seen before in our study of electronic theory of solids. This is probably the first instant where a number non-conserving wave function was used to study a problem, and it shows that the BCS wave function is actually a wave function with a fixed phi phase, whereas you can pick out the particular number wave function part of the out of the wave function, you can pick out the particular part which has a certain number, definite number, and that is how it is done. And that is a beautiful aside I thought I should show you. It was first shown by Anderson, and its consequences are terrific, because if phi is fixed, then numbers can fluctuate. For example, if you take two superconductors, one has a phi 1, another has a phi 2, then they will try to have the same phase, because BCS wave function has a fixed phase. So, the entire system will try to become a superconductor with the same phase, right. Both are superconductors, so they will try to become the same superconductor, and they will match their phases. By changing phase, that means one of the phase or both the phases will adjust, they will change, that means numbers will fluctuate, that means number of pairs will move from left to right or right to left. That means by just putting two superconductors together, you can have a flow of current, and that is actually something that happens, and that is shown to be beautiful, that has tremendous applications, and that we will come towards the end of this lecture. So, let me just go to a topic which is required when we do electrodynamics of a superconductor, and because you want to understand what happens when a superconductor is placed in a magnetic field, and so that requires a treatment which is a bit different. We do not approach that problem from microscopic theory. For that, an approach based on Ginzburg-Landau theory is the best approach to follow, and that is what we will start now. So, our aim now is a bit different. What we are trying to work out now is to see what happens if a superconductor is placed in a magnetic field. Now, of course, we know that there is a Meissner effect. So, all the fields will become expelled. But in a remarkable paper, Abrikosov showed in late 50s, around 57, that that is not the case always. There is a state possible which is where the magnetic field can penetrate a superconductor depending on the conditions that we will outline, and that in that state superconductivity and magnetic field, magnetic flux inside the superconductor coexist in the sense that the flux actually penetrates in some tube like structures which are called vortices, and the superconducting order parameter goes down to 0 at the core of these vortices, and the rest of the situation outside this vortex, the superconductor remains a normal superconductor, just like the superconductor it was. But this is a unique new situation where Meissner effect is in a sense not followed, but the vortices, the magnetic field enters the superconductor in vortices. So, and that vortices, these tubes are not random. What Abrikosov showed is that they form a lattice of their own. So, that is like a crystalline object of vortices of these tubes. Okay. So, let me start from Ginzburg-Landau theory. Instead of writing this long beast on the right, let me just give you an example of Ginzburg-Landau theory starting from absolutely simple arguments. As I said, suppose there is a phase transition as a function of temperature. We know that there is something called an order parameter. I mentioned that something which is non-zero below Tc. So, suppose this is Tc. So, this I called order parameter. It can be magnetization for magnets, it can be the density for a liquid to gas transition, and so on and so forth. So, this we have seen that this order parameter which is non-zero in the ordered state, and like in spin's case we did it was magnetization or staggered magnetization for antiferromagnet. This generally follows a structure like this, behavior is like this, sorry. So, it follows a behavior which is that it goes down to 0 at T equal to Tc. Okay. So, continuously goes to 0. So, in superconducting case also, as we showed that the superconductivity for example goes to 0 at T equal to Tc. Okay. So, that means we should be able to write down an order parameter for the superconductivity which is 0 beyond Tc and non-zero below Tc. Okay. Above Tc it is 0, below Tc it is non-zero, and Ginzburg and Landau were able to write down an order parameter which is like this. So, they said that let us think of a superconducting wave function which is like this pseudo wave function, you can call it, whose square gives me the superconducting density. Okay. So, and because the psi can be complex, so I put a mod there, and mod psi square gives me Ns, the superconducting density. Now, superconducting density, this is called the superfluid density or superconductor densities, whatever. So this N sub S, the superconducting component of the density is 0 above Tc. So this is 0 for T greater than Tc, and finite non-zero for T less than Tc. So this is a good choice for an order parameter. So then mod psi square is the order parameter that they chose. Now you can easily see that suppose I have a free energy, for example, F equal to the, so close to, this is done very close to Tc. So that I can expand this around the normal state free energy plus some a by 2 m square. M is, suppose m is my order parameter, plus b by 4 m to the power 4. Okay. So this even powers are taken because I assume that there is an m minus m symmetry, which is, for example, in a ferromagnet we have seen that without a magnetic field that symmetry exists. So in that case f minus fn close to the transition, because close to transition I can expand in this polynomial because m is extremely small. At Tc m goes to 0. So this is the result, right, a by 2 m square plus b by 4 m to the power 4. I still do not know what a and b are. Now what let us just draw it. For b has to be greater than 0. You see, if b is not greater than 0, then m will become infinity, because then the free energy will be, you will gain a lot of free energy by making m going to large, because b is negative. That is the highest coefficient of the highest power. You should not do that. That is clear from this graph that I am drawing. So f minus fn, let me set fn to be 0. I mean, I am starting from fn equal to 0. I set my free energy scale there, and versus m, if you look at it, for a equal to 0, b equal to 0, sorry, a greater than 0, and so this is a greater than 0. Remember, b is always 0. Otherwise, if a and b were both negative, I would get a curve in this direction, right? And then you can see that the m will choose values at infinity, so that this energy goes to minus infinity. So that is not allowed. That never happens. So I have to have a positive b, which is this. Now in positive a, this is what? So the solution is minimum is at m equal to 0, right? So that is the solution. Now I make a less than 0. Then what will happen is that you will see that the curve now looks like this. So the m equal to 0 solution, which was minimum, now is no longer the minimum. The minimum has shifted to m naught. How much is m naught? I can easily find out. I can just do del f del m equal to 0. So that gives me a m plus b m cube equal to 0. So m equal to 0 solution is not what I am looking for, and a is negative. So m square equal to minus a by b. A being negative, minus a is positive. So this is basically mod a by b. So that is the solution m naught. This is, of course, symmetry exists, plus m naught and minus m naught are degenerate. So this is what Landau and Ginzburg started using, that depending on the sign of a, you can go from a m equal to 0 order parameter 0 state, which means you are above Tc, disordered state, to a state which is below Tc, which is a finite m, which is a finite value of the order parameter. And what they did is that simplest choice is that take a to be such that it is some alpha times t minus Tc. So it is greater than 0 for t greater than 0, t greater than Tc, and less than 0 for t less than Tc. So it mimics this situation, right, that a will become negative as your t goes below Tc, and then immediately you will find that you have a finite m solution, and this gives, you can solve for m as I have just done, and this will give my t minus Tc to the power half. So that is this. So m versus t m versus t will have a solution of this kind. Again, t equal to Tc, it will go to 0, this. Okay. So that is the that is what Landau and Ginzburg did, and that is what we are going to follow. So we will set mod psi square equal to 0 above Tc, mod psi square less than 0, mod psi square finite below t equal to Tc. So that sets up the theory for Ginzburg and Landau, and that is how they did it, and that is how superconductivity in a magnetic field is done, and that is what we will follow from the next class.